In this section, we're really focused on putting all the pieces together from 4.3. So in the last section, we talked about what does the first derivative tell us, what does the second derivative tell us, how do we find local extrema and concavity and inflection points and all of that stuff. Here we're going to continue to do all of those things. We're going to bring them all together, and then at the end we're going to say, okay, what does this all tell me about how my function looks? What does my function look like at the end of this? Here are some graphing guidelines that we're going to loosely follow here. For the most part, this is stuff that we already know how to do. So you'll find the domain of your function, right? You want to find out where your function is defined, where it's not. Here we can use symmetry if possible using what we know about even and odd functions. So for example, if you're working with an even function, then f of negative x is equal to f of x. Then that function is symmetric about the y-axis. If you have an odd function, in that case f of negative x is equal to negative f of x, then your function is symmetric about the origin. I'm not going to be using symmetry all that often. It can be a very powerful tool and it can save you a lot of time, but more times than not, our function will not be symmetric. And I think that it's difficult to recognize. It's not something that we've practiced in a long time. We haven't talked about it in this class, but I'm assuming you've probably seen it at some point in another math class. So that's not something I want to spend a lot of time on. But other parts of this we have seen plenty of. We found our first and second derivatives. We found critical points and possible inflection points. Finding intervals where your function is increasing and decreasing and concave up and concave down. Local extreme values and inflection points. Finding asymptotes. We may not have done asymptotes in a long time, but we talked about those in chapter 2. Same thing with determining end behavior. And then this is really the new step. It's graphing the function. It's putting all of this together at the end in a way that makes sense. So the first example that we're going to look at, these are actually one of my favorite type of problems. I can promise you that I will ask a question like this on the exam. It says, suppose that f is continuous on negative infinity to positive infinity. We want to summarize the information using a sign chart and sketch a possible graph of f. So here, I'm actually giving you a lot of this information. In other problems that we do after this, kind of all of this information right here, you're going to have to go and find that information. But right here, you're just given it. You're saying, oh, you said, okay, here's all this information about your first and second derivative. I know that it's continuous on negative infinity to positive infinity. Just make the graph for me. It's really just that last step. And I'm kind of oversimplifying it a little bit because we do need to take this information and kind of digest it and see what it means. Kind of write it in a way that's a little bit easier to understand, a way that makes more sense. And in particular, I'm going to use a sign chart. I think that's incredibly helpful. So they give us a bunch of different intervals, first of all. I'm kind of looking at these guys over here to start off. We're given negative infinity to 0, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to infinity. So I'm going to create a number line for both my first derivative, f prime, and actually here. Let me give myself enough room because there's going to be a lot happening here. Here's my number line for my first derivative. Here's my number line for my second derivative. We seem to have changes at 0, at 1, at 2, at 3, and at 4. Maybe not both of them are changing, but something's changing. And we're just going to fill out as much of this sign chart as we can. I think it'll help us graph a possible version of f. It'll come in very handy. So let's start right here. I'm actually going to look at the intervals first. So I know I'm on the interval negative infinity to 0. So I'm talking about this leftmost interval here. Well, what do I know? F prime is less than 0. So my first derivative is negative. So I'm going to make a note of that. My first derivative is negative, means my function is decreasing. and f double prime is greater than 0. So f double prime here is greater than 0. My second derivative is positive, which means that my function is concave upward. And I'm just going to continue to fill out as much of these number lines as I can. So next, if I look at 0 to 1, I'm just moving to the next interval over. I know that f prime is greater than 0, so now my first derivative is positive, which means that my function is increasing. And I know that my second derivative is still greater than 0. So my second derivative is still positive there. It's still concave upward. I haven't seen any change in my second derivative yet. Next, on 1 to 2, that's this interval right here, the next one over. Well, I know that f prime is greater than 0, so f prime, my first derivative, is greater than 0. In other words, it's positive, means that my function is increasing. And I know that f double prime is less than 0. So f double prime is less than 0, it must be negative. So now I have a switch to a concave down graph. Next, 2 to 3. So what do I know there? F prime is less than 0. So f prime is less than 0. It's negative. My function must be decreasing there. And f double prime is also less than 0. So my second derivative, still negative, still concave down. 3 to 4 next. Let's look. F prime, first derivative, is negative, so we're still negative over here. My function must be still decreasing. But I have a change in sign in my second derivative. F double prime is greater than 0, so it's positive there. My function must be concave upward. And finally, 4 to positive infinity, that rightmost interval. My first derivative is greater than 0. My first derivative is positive. It's increasing. F double prime is greater than 0. F double prime is still positive. My second derivative is increasing as well. Holy moly, there's a lot going on here. I would next look at these numbers here. I would look, well, what's going on in each one of these numbers? So let's say here at 0. Let's look at 0 first of all. My function changes from being decreasing to increasing. At 0, I have a local minimum. What's happening at 1? Well, at 1, this time my first derivative stays the same sign, but my second derivative changes sign. We said if our second derivative changes sign, if you have a change in concavity, that is called an inflection point. All right, we'll continue on to 2. At 2, I see this change from increasing to decreasing. That must be a local maximum. At 3, my first derivative stays the same. It stays as a negative value. And here, for my second derivative, though, that will change sign from negative to positive. So I have another inflection point. 4. Let's see, at 4, my second derivative stays the same, but my first derivative this time, again, I have this change from decreasing to increasing. I have another local minimum happening at x equals 4. I think this gives us a lot of information then about what our graph should look like. So let's go ahead and sketch a possible version of this graph. 1, 2, 3, 4. And I say possible version because they haven't given us any information whatsoever about the y value. So this graph can exist at any y value that you want. You don't even necessarily need to number your y-axis. I'm not going to scale it. But the behavior should all be the same relative to our x-coordinates here. So let's see, I'm going to sketch my function in blue. What did we say was happening at 0? I'm actually going to label these points right here. At 0, we said that we had a minimum happening, so let's make a note there. At 1, I have an inflection point. At 2, I have a maximum. At 3, I have an inflection point. And at 4, I have a minimum. This is not something that you're required to do, by the way. I think it's just a helpful tool that you can use. So let's see. The other thing I would look at, I tend to think that the second derivative, concavity is not something we have spent as much time talking about, and we have not spent as much time talking about the second derivative in general. But I actually think concavity is a very powerful tool. It gives you a lot of information about what the graph looks like. So I actually like to make a special note of the concavity as well. So I'm going to make a note down here. In this section, we said it was concave up. So concave up. Then in between these two inflection points, it was concave down. And then after that, it was concave up once again. So I sort of take these inflection points as I go. I'm just going to plot a point right there at 1 comma whatever. And I say, okay, well, my function on that interval was concave up, and I have a minimum. Concave upward graphs, we can actually kind of visualize those. It's concave upward, it's opening upward. Visualize a parabola if you need to. So my function is concave upward. I should hit that minimum right there at 0. And then after that, it's concave upward. It's going to follow the behavior of a graph that is concave upward. What happens next? So we should hopefully be able to say that concave upward shape right here. Well, what happens next? Next we switch and we're concave down now, and visualize that concave down shape, that y equals negative x squared shape. So we're concave down, so we should be kind of opening downward now, but I should have that maximum there at x equals 2. So I'm actually going to draw that in. I'm going to hit that maximum right there, and I didn't really do a good job of doing that. Let's say our maximum occurs right there. I think that'll be easier to work with. So our function should look something like this until we get to this inflection point. And this one's a little bit more subtle. We should see hopefully here is something which is concave up, and then here is something which is concave down. This point right here is probably not a point that would jump off the page at you and grab your attention, but it is a really important point here. And let's see, we need to make it all the way to 2, and okay, and then what happens? Then it switches, now it's concave upward. We can have that concave upward shape in our mind, that parabola-like shape. Here, this one might go down a little bit further just from the slope of the tangent line that I've drawn here. So perhaps it looks something like this. I've got a minimum, I've got a minimum there at 4, so perhaps it looks, not happy with that. Perhaps it looks something like this. We've got our minimum right there at 4, and then after that, it continues on as concave upward. So again, we should see this almost gradual shift. It's a very subtle shift between being concave down right here and being concave upward right here. These are problems that I really like. I can promise you that I will ask at least one question like this on the exam because you have all of the information already here. Finding that information is a whole other ordeal that we'll get there. We'll talk about that in the next video. But here you're given all of this information. You just need to make sense of it and then put all the pieces together. I probably won't ask you to graph a function start to finish because there's so many places that problem can go wrong. I'll still be finding problems to, ask you where to find your local extrema, find your inflection points, determine where it's concave up and concave down, all that jazz. But take a look at a few of these problems. I think they're excellent study tools, and it really captures, I think, the most important points of this whole section, which is putting all of the pieces together.